In this problem, we're looking at the motion of two rigid bodies. We have this arm OB, which is which is pinned to ground at O. It's a non-homogeneous bar, so its center of mass G is not in the middle, but it's at 0.3 L from the left side. The disc is pinned to in C of the bar. The disc has a radius of R, and the system is released from rest. And if that disc is pinned to the arm, what is the angular speed of the link OC after OC has rotated in a clockwise sense through an angle of 90 degrees? We're looking for change in velocity for change in speeds for a change in position. So we will definitely consider the work energy equation. The work energy equation says that for the most part we want to be making the system as large as we can. So I'm going to draw a free body diagram of the whole system. So that's going to be the disc and the bar together. Like this, the forces that we have acting, that's going to be the weight of the disc. The weight of the disc is going to be, let me call that big M, G. The weight of the bar is going to be small m, mg. We have reaction force there of OX and OY. And so what we want to do here is figure out which forces, if any, do non-conservative work. So OX, OY, they don't do work because they act at a fixed point. MG, for each case, that does work, but we're going to include that in V. So therefore, there are no forces left that are going to be doing work. So when we write down the work energy equation, the work term in going from position 1 to position 2 is a 0. It says that the system starts out from rest. So T1 is a 0, initially at rest. I'm going to put my datum position through point O. So at that position, the gravitational potential for both is a 0. So for T2 is going to be equal to, let's write down the kinetic energy for the bar. I'll reference that to point O. So it's 1/2 I-O omega OC squared. So this is for the bar. And for the disk, I'm going to write that as 1/2 the mass of the disk, the speed squared of the center of mass, plus 1/2 mass moment of inertia about C omega for the disk squared. So this is the total kinetic energy there for the disk, where I.O., that's given to us in terms of the radius of gyration K0. That's going to be M K0 squared. And the mass moment inertia of the center of this homogeneous disk, that's going to be 1/2 M times R squared. So that's what we have for that. V2, the potential for the bar rotating up through a 90-degree angle is going to be a minus mg 0.3 L. And then for the disk, it's going to be minus big mg times L. So we have all the 5 parts. They go together into our kinetic potential work energy equation. So that's going to be T1 plus V1 plus the work done in going from 1 to 2 is equal to T2 plus V2. Again, it was starting out from rest. My datum passing through there. There's no work being done. So we have just a 0 is equal to 1/2 I-O omega OC squared plus 1/2 big mvc squared plus 1/2 mass moment of inertia of the disk omega d squared minus the 0.3 mgl minus big mgl as that. That is our work energy equation for the system. Unfortunately, we have, as it's written here, one equation and 3 unknowns. That's where kinematics usually comes to our rescue. So what kinematics do we need? Well, the first one here is that since C is actually on OC as well as on the disk, we can say that the speed of C, with the bar rotating about 0.0, is simply going to be L times omega OC. So that's one equation. That's going to go in right there. But the other one here, what is omega D? Well, omega D, if we draw a free body diagram of that by itself, the forces that we have acting on this are the mg as that. There's going to be some reaction forces from the bar. We'll call that Cx and Cy. The point being is that all these forces act through the center of the disk. So to get the kinematics, we're going to use a kinetics equation that says the moment about C for this disk is a 0, which says that the alpha for the disk is a 0. If alpha is equal to a 0, then the omega will be, since it starts out from rest. What this means is if there had been some initial spin for the disk, that spin would be unchanged because there's nothing in that bearing at C to cause that to change. So therefore we have the equation to solve now is the equation above, but now we have 1/2 IO omega OC squared. The VC we said was L omega OC squared. The omega D is a 0. On the right hand side, what we have is a plus, once we bring it onto that side, 0.3 lowercase m plus big M times GL. So from this single equation, we will solve for omega OC, like that. So this problem was one with using the work energy equation. We draw a free body diagram of the system as a whole. Keep as many forces internal as we can. The work energy equation gave us 3 unknowns. So we had to appeal to kinematics. We needed to be able to relate the speed of the center of the disk back to the angular speed of OC. And we needed to make the observation that that disk on the end, it moves, the center of it moves through a circular path, but the disk itself does not rotate. Its orientation remains unchanged. That was a key observation. With those 2 pieces of kinematical information, we then solved the problem.